Hello everyone, my name is WenYu from Nanjing University of Posts and Telecommunications. I'm glad to share our work on multi-view 3D surface reconstruction, GSNSR, improving neural surface reconstruction with geometric and color priors from 3D GS. I will cover 4 parts: background, method, experiments, and conclusion. Let me start with some background and the key challenges we face. There are 2 main approaches to 3D surface reconstruction. The first is implicit neural SDF, such as News and NeuroAngelo. It represents the surface as the zero-level set of a signed distance function. This gives high geometric accuracy, producing smooth, coherent meshes. The downside is the slow training, and it tends to create spurious volume. The second is 3D Gaussian splatting, 3D GS. It represents the scenes with a set of anisotropic Gaussians. Rendering is extremely fast, but it's a discrete representation, which makes it hard to extract a smooth surface. So, one is strong in geometry and the other is strong in appearance. They are naturally complementary. We treat a pre-trained 3D GS model as a geometric and photometric prior and use it to guide the SDF optimization. Our goal is an accurate surface, so we approach it from 2 sides: the outer contour and the inner detail. First, how do we reconstruct the outer contour? The key issue is geometric ambiguity. Volume rendering places no constraint on empty space. It only checks whether the color accumulated along each ray is correct, not where the density sits. In difficult regions, the network takes a shortcut. It fits a false volume in front of the true surface and gives it a near shadow color, so the rendering still matches. The color is consistent, but the contour is distorted by these floaters. Second, how do we recover the detail? The natural idea is to use 3D GS to guide the SDF, but the 2 representations are very different. 3D GS is discrete and appearance first, while the SDF field is continuous and geometry first. Existing hybrid method bridge them only at the loss level through depth or normal consistency. This alignment is fragile. Once the 3D GS depth is noisy, the errors propagate into the SDF, and optimization only makes it worse. So the real question is how to fuse them without carrying the errors alone. The first module targets the contour. Volume rendering has a blind spot. The photometric loss only matches the surface color, not how density is distributed along the ray. So floaters and spurious density appear in front of the surface. Depth and normal consistency can align the surface, but never penalize opacity that sits in front of it. Our fix is an explicit free space prior. The 3D GS depth tells us where the free space is, and epsilon serves as a tolerance margin to accommodate the errors in the pseudo depths. This one. This step needs little precision. The depth only has to roughly tell us that the space in front of the surface is empty. Okay, here is the pilot. On the left makes it easy to see. The horizontal axis is the position T, and the vertical axis is the rendering weight. And T pseudo is the 3D GS depth. The ray splits in free space, surface, and background with the gray margin, giving tolerance for depth error. The red curve without the free space loss shows small peaks before the space at A and B. Those are floaters and full density. The blue curve with free space loss, this one, pushes those weights to near zero. So the weight concentrates on the main peak, C. It's the true surface. This one is C. But the pseudo depth is not always trustworthy, so we should not apply the constraint equally. We compute a depth confidence for each pixel at the product of 3 terms, each guarding against one kind of unreliability. The first is support. Against sparse or missing depths, it counts how many valid depth pixel lies in a local window. The second is consistency. Against noisy or jumps, it checks whether the local depth is smooth. The third one is view reliability, this one. Against grazing angles, depth changes quickly across the image and is often unreliable, so we measure it with the image space depth gradient. So multiplying them gives a per pixel confidence, this one. Stronger where the depth is reliable and relaxed where it's uncertain. This suppresses floaters without injecting wrong geometry from inaccurate depths. The images on the right shows it. When you look straight at the surface, depth is stable, so it gets high confidence. When you look at it from the side, the depth jumps around, so we trust it less. The second module targets the detail. We fuse 3D GS features into the SDF network at the architectural level. There are 3 questions. How to aggregate the features, which Gaussians to use, and how to fuse them. And our answers are exactly our 3 differences from Splat SDF. Okay, the first one is how to aggregate. We design a decoupled aggregator. 3D GS already separate geometry from appearance. Geometry is the center and covariance, and appearance is the base color and SH coefficients. We follow this same structure and use 2 independent aggregators. The geometry aggregator here. The geometry aggregator takes the hash encoding of Gaussian center together with its covariance and output geometric features. The color aggregator takes the base color and SH coefficients and outputs the color features. Okay, the second question is which Gaussians and where to fuse them. This comes down to the anchor. The anchor decides where features are injected, so it must land precisely on the surface. We locate the anchor from the SDF field itself, a long array. If 2 adjacent samples have SDF values of opposite sign, there is a surface crossing between them, and we find the position by linear interpolation. This keeps the anchor consistent with the SDF being optimized. Better geometry leads a more accurate anchor. Anchor is here, which leads to more reliable guidance. It's a positive feedback loop. Third, how to fuse the features. At the anchor, we find nearby Gaussians and aggregate their features with a spatial weight. We map it back to the sample points. We distribute it by distance to the 3 samples that bracket the intersection through a separate auxiliary channel. Okay, in the figure, the black arrow is the view direction. The green point here is the intersection. The 2 yellow points are its nearest samples, and the colored ellipses are Gaussians we use. This one, colored. Here, D1 is the distance from the first sample to the intersection, and D2 from the second. The sample is ideal. The closer a sample is, the higher its weight, exactly as expressed by the formula on the right. Okay, this is the full GSNSR framework. The input image first produces 3D Gaussians. The geometry and color attributes pass through the 2 aggregators. They are then fused by distance weighting. Finally, differentiable volume rendering produces the image. The free space loss handles the empty space in front of the surface, and RGB loss handles the rendered results. We also keep the other losses from our baseline instant NSR. Now let me show some results. Here is the qualitative comparison on DTU dataset. On scan 83, the door's beard is a high frequency detail, and we recover it from more completely. This one. On scan 110, we recover clear boundaries and smooth contour. This one. To show what each module contributes, we run an ablation experiment with 4 configurations. The splat SDF style variant, one without the free space loss, one without the decoupled aggregator, and the full GSNSR. The splat SDF style variant is modeled after splat SDF, but keeps the free space loss. It uses a coupled aggregator that bundles 4 3D GS attributes into one set of features and takes 3D GS steps as the anchor, and uses replacement fusion. The variant without free space loss keeps GSNSR network design and only drops the free space loss. The variant without decoupled aggregator switches to a coupled aggregator. Okay, on scan 63, a group of smooth fruits. The splat SDF variant anchors on the 3D GS and produces the most obvious depression. Moving to the SDF intersection anchor and distributing by distance clearly reduce it. And the decoupled aggregator further keeps appearance out of the geometry branch. The full GSNSR gives the most smoothest surface. LEGO has a complex structure. Removing the free space loss let floaters appear. They feed photometric signal and give the highest PSNR, but corrupt the geometry and give the worst chamfer distance. This one. So the free space loss trades a little appearance fitting for geometric accuracy. This is the mask. The mask only separates foreground from background. It doesn't cut out the area under the LEGO chassis. That tells us the free space loss is actually enforcing this constraint. MIG has a high-frequency lattice. The free space loss, the splat SDF style variant almost collapses. Without the free space loss, the cavities filled with spurious density. The full GSNSR recovered the open lattice while suppressing the extra volume, giving the best chamfer distance and PSNR. Okay, for the contour, the confidence-aware free space loss turns the 3D GS pseudo-depth into a per pixel reliability-weighted prior. For the detail, the SDF-guided feature fusion places the anchor at the ray surface intersection, uses a decoupled aggregator to handle geometry and appearance separately, and distributes features by distance. We also see three limitations. First, we only downweight the depth as a soft prior. We do not correct it. So when the depth is badly wrong, a slight geometric bias remains. Future work could active correct the depth prior instead of treating it as a fixed signal. Second, we build on the original 3D GS, which leaves many floaters. We would like to plug in a more accurate Gaussian representation. Third, our network is designed for the object level synthesis. Future work could use hierarchical networks to extend its capacity. Thank you for listening. I would be glad to continue the discussion by email.
Thank you for the nice presentation. Are there any questions? Then I will just start with one of my own. So sometimes if you have Gaussian reconstructions of real-world objects, you end up with like very semi-transparent, like large Gaussians. Are you able to handle those, or are they gonna like confuse the depth prior?
For those large Gaussians, we actually trust less in these regions, in these depths, in this region, and the free space loss and the weight of the free space loss is down. So it will not disturb the reconstruction.
Okay, thank you. Well, then let's thank our speaker again.